Hello, and welcome to this presentation called Parametric Amplifiers for Quantum Computers, a necessary component for quantum computers. Let me begin this talk by talking to you about quantum computers. Quantum computers are a different kind of computer. It's not a supercomputer, which is a common misconception, but rather a different kind of computer that calculates things in a different way. And these can potentially efficiently find new drugs, find climate change solutions, break internet security, and so on. It's beyond imagination. And the reason for this is that on quantum computers, you can run something called quantum algorithms. And quantum algorithms can, for certain problems, be much faster than the classical algorithms. So to give an example of this, let's look here at, we have two we have a classical algorithm that takes about 10 seconds to run and a quantum algorithm that takes about a minute to run. And now you might say, well, that doesn't sound like a speed up. That sounds like it's much slower, which it is. But this is for a very small problem size. And the strength doesn't come necessarily at every problem size, but rather when you start scaling problems up. So if we start scaling this problem up, at some point, the two algorithms would take the same amount of time. So here, 2 minutes. But then when we keep scaling the problem up, then there will quite soon be a clear advantage in using the quantum algorithm. So here it would take 10 minutes for the quantum algorithm, but 330 years for the classical algorithm. And then if we scale it up even further, the difference becomes even larger. So here, for example, 11 minutes for the quantum algorithm, while 3,300 years for the classical algorithm. At Chalmers, we research something called superconducting quantum computers, which is a certain kind of quantum computers. And a superconducting quantum computer is placed inside a cryostat. A cryostat is essentially a big fridge, which has different levels like this at different temperatures. And at the very lowest one, which is at 10 millikelvin, which is almost absolute zero, we have the quantum processor with all the qubits, which are the building blocks. And then we have lines coming in and we have lines coming out. And to calculate something, we essentially send microwave pulses down on these lines. And then the quantum processor can calculate something. But to know the result, at some point we need to read a qubit out and to know if it's in state 0 or state 1. So then we send a readout pulse, goes down, it interacts, and then it comes out with the information. And now we start approaching the problem here. So this pulse that comes out, we can plot it on an IQ diagram. Essentially, we translate the pulse into two voltages, and then we plot them. The problem is that the pulses are so small in amplitude that if we were to detect them right away, we would just get data points at 0 voltage for both states. So we couldn't tell a difference. So we need to amplify them. So we will have an amplifier chain coming out of the cryostat. And now there's a new issue. And to illustrate it, we would need to begin by zooming in. So let's go down inside the cryostat. We cannot go there for reals, but let's imagine that we could measure in there. So now we're inside the cryostat, and the two different states, 0 and 1, are shown like these two dots. Now, if we could measure inside the cryostat, then we would get data points spread out a little bit around these two dots. And the reason for this is because of something called vacuum fluctuations, and or rather background noise, we could call it, which is a kind of noise that we cannot get rid of. So we will get a little bit of a spread, but it's fine. We can still distinguish the two states. We can illustrate this spread of the two states as two blobs like this. But this is inside the cryostat, and now we would need to amplify this to become larger. So after the first amplifier, the two blobs would look something like this. And now they've grown in size, and that has to do with the noise added by this first amplifier. And now when we amplify them with a second amplifier, which also adds noise, then the two blobs would overlap like this. So now if we actually measure out, or rather take the data points that these two blobs correspond to, you will see that there are data points overlapping in this region in between. So in short, due to the noise added by these two amplifiers, there will be an overlap of the two states, and then we cannot distinguish 0 from 1. For example, this red dot here is actually belonging to this state, state 1, but it is closer to state 0, so when we measure it, we would think it's state 0. But it's only closer to state 0 because of the added noise. So let's go back inside the cryostat. But now imagine that the first amplifier doesn't necessarily amplify as much, but it adds less noise. So then after the first amplifier stage, we would still have quite a clear separation of the two states. And then when the last amplifier amplifies, even though it still adds the same amount of noise as before, the states are now well separated. So when we actually look at the data points, we would see that even though they have a spread to them, we can distinguish the two different states. And that is what we want to achieve. We want to achieve an amplifier, the first amplifier in the amplifier chain, and that this amplifier only adds the smallest amount of noise that is necessary. And to build such an amplifier, we will build a so-called parametric amplifier. And to give an example of what a parametric amplifier is, let's take an example where we imagine a ball in a pit. And this ball is the signal that we want to detect. And now imagine that this ball oscillates with so tiny oscillations that we can't detect it. But now imagine that the pit in question, that we can change the curvature of it like this. So we have a ball that oscillates with small oscillations inside the pit, and we can change the oscillations of the pit. So now if we time the change of the pit to the ball's oscillations, such that the ball has a little slope when it goes uphill and then much slope when it goes downhill, then it will start oscillating more and more. And this is essentially illustrating how a parametric amplifier works. You just have some parameter, in this case the curvature, that you change back and forth, you modulate it. And that way you make something small, in this case the little ball and the ball's oscillations, to grow. In reality, of course, I don't work with a ball and a pit, but rather I make these tiny chips that I then put inside these boxes. And then I put these boxes inside the cryostat. Here you can see an actual cryostat rather than the sketch that I showed you earlier. But the details of this is a story for another time. Thank you.